All right. I'm gonna get started. We are already like 3 minutes past 5:30. So what we'll do today is the first thing I'll do is I'm gonna write that floating point number conversion thing that you guys have been working on for the past week and a half or so. Okay, because we first started off with a negative exponent and then we move on to the positive exponent. So I'm gonna finish that part, and I'm also going to finish the normalization part. Okay, which you do not have to do, but I do want to finish that just so that you guys can kind of see, what it is about, and also, to see that how it works. Okay, so that's the first part of today's lecture, and then the second part is the continuation to talk about D flip-flops. Okay, so we'll probably transition to the concept of a register, which is basically a multi-bit D flip-flop, and then continue to talk about other components inside the processor. So that's how we're gonna be able to talk about the inside of a processor eventually. All right. So before I start here, are there any questions that you need to be answered? No. Okay. All right. So we're gonna get started here. And this is the most enjoyable part of teaching this class, which is I get to do a little bit of programming. So I'm going to use the same tools that you guys use, okay? Because that seems reasonable. Except the file that I have is no longer here, so I need to re-download it. So go back to Chrome. Go back to up a little bit. Okay. Negative exponent. And do a preview so I can get to the link of that file, which is here. All right. Oh, I already have a copy, so I probably have it already unzipped somewhere in the same folder, probably. There we go. And I need a command line to unzip the file. All right, so that creates a folder called 11 in my temp folder. Now I go back to here, and I know where to find it. And 11. And we have to open the CBP file, which stands for Code Blocks Project. And here's the project. So I'll give it a number to process. So go to Set Programs Arguments. And remember, it has to start with -n, and then the actual number I wanted to process, 1.23e. Okay, do you guys want to deal with negative exponents first or positive exponents first? Positive? Okay, all right. So let's make sure that it exceeds what a double can represent first. I mean, what a 64-bit unsigned integer can represent first. Okay. Set everything to be okay. Go to the one file that I need to process, which is this one. And we'll start from here. So the first thing is, as long as pn-exp10 is greater than 0, I'm going to stick in this loop here. And I can almost write the other one at the same time, which is kind of the opposite. As long as the exponent of 10 is negative, stay in the loop. And I do not need a conditional statement, because when the first loop exits, exp10 is going to be 0. So there's nothing the second loop is going to do. Does that make sense? Because the objective is to make exp10 the member 0. 0 is neither greater than nor less than 0. Okay? All right. But one thing at a time, we'll deal with this one first. So if the exponent of 10 is greater than 0, then one of these steps, okay, is going to increment it. Oh, decrement, so that it gets closer, right? But in order to decrement the exponent in base 10, what do you think I need to do first? I have to do something about the mantissa so that the adjustment to the exponent in base 10 is really just to counteract what I'm doing to the mantissa. So what should I be doing to the mantissa? Multiplication by 10. Okay. So multiplication by 10. This is just a shorthand of writing that. It is the same thing as exp10 times, it's the same thing as pn points to exp10 equals to, huh? Oh, mantissa, that's right, thank you. So we're multiplying the mantissa. Okay, so are we good? All right. But before we do this, we have to make sure that the mantissa has room for that multiplication by 10, okay? Which basically means as long as it does not have room, I have to divide it by 2 and then adjust exp2 accordingly. So the condition to do that is to say as long as the mantissa is greater than or equal to u int 64 underscore max, which is the constant that defines the largest number you can represent using 64 bits. But we want to make sure that this is also divided by 10 first. Okay, and there we go. So as long as it is greater than or equal to, I think it's greater than. If it's equal to, we should be okay. So as long as it's greater than, then we have to do something. So we have to make it smaller. So the way to make it smaller is to divide it by 2. But this time I cannot use the shorthand because I have to add 1 before the division by 2. So we have the same thing, and then this one, plus 1, and then divided by 2. So the plus 1 is here because we want to do a rounding instead of a truncation. Is that okay? You guys kind of remember that part? And the reason why we want to do rounding instead of truncation is because we do not want our errors to be biased. Okay, so this way we err this way sometimes, we err the other way some other times, so it's not going to be biased, which is basically erring in one direction all the time. So once we divide the mantissa by 2, we have to do something to compensate for that. So that is when we need to do something with exp2 or the exponent of 2. So in this case, if I divide the mantissa by 2, I have to add 1 to the to the exponent in base 2. Are we doing okay so far? Does it make sense so far? Okay, all right. So that's pretty much most of the code for the positive exponent code. But there's one little thing, okay? If you just think about it, okay? Let me see. Is that going to be a problem? Well, okay, so I need to make sure, okay, in the homework assignment, it says, you have to make sure that the mantissa has bit 63 set. Do you guys remember that part? Are we guaranteed, using this loop, that the mantissa would have bit 63 set? Is it guaranteed? There's no guarantee, right? No. So what we need to do, because we need to do bit shifting until the most significant bit is a 1. So now we have to, okay, so this is the pseudocode of the loop, okay? While the most significant bit is 0, do the following. What do you think we should be doing as long as the most significant bit is a 0? We should be shifting the number to the left. Is that making any sense? Okay. So how do we shift the number? Sorry? Say that one more time. Okay. So you can use the bit shift operator. That's one. You can also add the number to itself, because we are saying that it's the same thing as doubling. Okay. Or you can say that number equals to itself times 2. So all of those would do exactly the same thing. So I'm going to choose this particular way, mantissa that. Okay, once again, I'm using a compound assignment operator, which basically means it is the same thing as mantissa equals to mantissa left shift by 1. It's just a fancy way to say that, okay? But for those of you, who do not like to use bitwise operators, well, this will do the same thing, multiplication by 2. So is that clear? Does everybody understand why multiplication by 2 is the same thing as shifting to the left by 1 digit? No? Okay, what does 2 look like in binary? 1, 0, very good. Okay, so it's 1, 0. What happens when you multiply a binary number, which is a bunch of zeros and ones, by 1, 0? You have one more 0 to the right-hand side, and everything moves to the left-hand side by 1 position, right? Does that resemble something that I was about to do? Left shifting? That's why it works. Is that okay? Okay. So assuming that it works, okay, so assuming you guys understand, then we can continue, because you cannot just multiply the mantissa by 2, because you have to make adjustments to the exponent also. So in this case, if I'm multiplying the mantissa by 2, I have to decrement the exponent in base 2 to compensate, so that when you look at the product of mantissa and 2 to the power of exp2, it should still be representing the same value. Question? The mantissa is not in any quote unquote, it's not quote in any particular base. It is just a number. It's just a value. Look at it as a value, not as a number. Internally, it's already stored as a binary number. But from our perspective, just look at it as a value. So the objective is when you look at the product of the mantissa, 2 to the power of exp2 and 10 to the power of exp10, that value should never change as we make adjustments to mantissa, exp10, and exp2. So that's the bottom line. Is that okay? All right? Yep.
And would this part only be necessary if it doesn't, like, how we're checking if the mantissa
Right.
is larger than the highest number divided by 10?
Yep.
Wouldn't that only happen if it's not, like if it's smaller?
What if it's smaller?
Like if it's smaller than unit max and it never exceeds that value, like wouldn't we not have to do that?
Okay, so are you saying that by the time this loop is done, you have a number that is fitting all 64 bits? Or not fitting all 64 bits? Okay. Okay. So now the remaining question is this part here. How do I know the most significant bit is a 1, which otherwise is known as bit 63? So how do I know that mantissa has bit 63 set? So I'll ask you guys to give me 2 ways to answer this question. Yep. When mantissa is less than 2 to the power of 60, 50. No, this is not about 50. We want bit 63 set. Okay, but the idea is the same. Okay, so that works. Okay, so one way to answer this question is to say as long as mantissa is less than, basically, 1 left shifted 63 times. Okay, and if you prefer to use parentheses, you can do it like this. And I think you have to be extra careful with this one too, because if you just use a 1 here, what is the type of 1? What is the implicit type of the literal constant of 1? Yep. What is the type, not the value? What is the type? It's an int. Okay, very good. It's an int. But is int 32-bit or 64-bit? Do you know? You do not, okay? So if int turns out to be 32-bit only, and you are shifting it to the left 63 times, this becomes 0. So that's not good, okay? So one way to make sure that you are looking at 1 as a 64-bit number is to cast it first into a 64-bit number. Now we are looking at the 64-bit version of 1, and it is now safe to shift it to the left-hand side 63 times, so the bit 63 is now a 1. Is that okay? That's one way to do it. I'm going to leave this one on for a while so that you guys can look at it. But we can also do this in a different way. The other way to look at this is to look at the mantissa, and you do it the other way around. You shift it 63 times to the right, which means the most significant bit is now bit 0. And now you just say, actually, the syntax or one way to specify this is very simple. It's just like that. Okay, what does it say? I'm using a logical operator, and I have a syntax error. Yeah, because every time I do an open paren, I think it closes it automatically for me. I'm blaming it on the IDE, damn it. Okay, so when you look at the inside part of this expression, what is that saying? Pn points to mantissa right shift 63 bits. That means we are moving all the bits to the right-hand side 63 times. What happens to bit 63? It becomes bit 0. What happens to all of the other bits? They're gone. So the number is either 1 or 0. Okay? So if the number is 0, if this expression is 0, it means bit 63 is in fact a 0. If it is a 0, I want to stay in the loop. So I put a negation here, a logical negation. So basically saying, as long as the most significant bit is a 0, stay in the loop. So these two lines, line 25 and line 26 on the projector right now, they actually do exactly the same thing. Are we good so far? Somebody's going to say, but I don't like bitwise operators. Forget about all these bit shifting operation. Well, if you prefer, there's another way to say it. I mean, there are many ways to do this. Okay, so you can always just say, as long as the mantissa is less than, how do we specify 2 to the power of 63? But make it very easy. Well, I have seen some program using POW, P-O-W, which is a floating point number subroutine. That's kind of cheating. Okay? So one way to do this is to say, okay, we need 16 of these, 16 digits, so we need 12 more. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That's it. Because that also, so when you look at this hexadecimal number, all the digits are zeros, right? So we have how many zeros again? That should be 15 zeros. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the most significant hexadecimal digit is an 8. So 15 hexadecimal digits of 0 would account for how many binary zeros? 4 times 15 is 60 zeros. Very good. So bit 0 all the way to bit 59 are guaranteed zeros here. The most significant 4 bits are specified by this 8 here. What is 8 in binary? It's 1, 0, 0, 0. Cannot be a 4 because you cannot have 4 as a digit in binary. So it's 1, 0, 0, 0. So that means that 1 in the 8 is in fact bit 63. So this is yet another way to specify as long as the mantissa is less than 1 followed by 63 zeros, stay in the loop. So are we doing okay so far with these 3 different methods of basically specifying the same condition? Are we good? Is there any importance to kind of beat a dead horse over and over again? Yes, when you're making hamburger. But two, it is also important, okay? Why is this important? Because you may prefer to write this code using one of these three methods, okay? But what if you're reading somebody else's program? What if you're debugging somebody else's program? Well, the other person can choose other ways to express the same logic. So in your mind, you have to basically be able to equate one method to be the same as the next method, to be the same as yet the next method. This is why it is important to be able to look at the same thing in different ways or come up with different expressions to express exactly the same thing. Is that okay? Making any sense? All right, cool. So which one do you want to actually use in this program? I'll just comment out the other two. Well, since you guys do not have a, huh? Number 3, you want to use number 3? Okay, we'll comment out the other ones. There we go. Now with the number 3, it's always better to just cast it to, because otherwise it is usually signed, and we want to make sure it is considered as unsigned. Okay. All right, so I think the program is ready for testing now. Okay, so let's go ahead and test it. We put a breakpoint at the end of the subroutine. Okay, I click at the wrong place. Right here. There we go. And then we just go ahead and try to run it. All right. Oops. Right here. Click first. Print whatever PM points to. And it's giving me something that seems to make sense. Okay? But is it actually correct? Is that answer correct? How do we know? How do we check? Yes? Yep. Okay. So to do that, I might need a scientific calculator. So I will go use, I use a spreadsheet. By the end of this semester, you guys will be very tired of spreadsheets because I use it for everything. Okay, so we'll copy this number first. Okay, so double click, copy, and paste it here. And then we'll copy and paste the exponent in base 2 and paste it here. And now we want to look at the mantissa, which is this number here, times 2 to the power of 70, which is this number. And we got 1.23 times 10 to the power of 40 back. So that works. Are we doing okay so far with the positive exponent? So we work on the negative exponent. Okay, all right. So now we work on the negative exponent, which is kind of going in the opposite way. So the way I write my program is non-linear, which means I look at this and go like, okay, eventually what I really want to do is to increment exp10 by 1 for each iteration. But to do this, to allow me to do this, we have to be dividing it by 10 first, because the addition of 1 to the exponent in base 10 is to compensate for the mantissa being divided by 10. Is that okay? So I look at that and go like, okay, so we need to look at the mantissa and say the mantissa we need to do the rounding, so that's why we have to add 5 first before we divide it by 10. The floor does not need to be explicit because integer division is automatically truncating. Did I miss something? Oh, parentheses again. All right. But if I need to do something like this, there's a division by 10, and I want to maximize accuracy, that means I want to maximize the mantissa before I do the plus 5 and division by 10. So that means I have a loop here, okay, while mantissa is not large enough, okay. I'm just using comments here, and then I'll specify the code later. Okay. What do I do in this loop here? How do I make the mantissa bigger and bigger and bigger? multiply by 2. Okay, very good. So we can say, let's multiply the mantissa by 2. So once again, I got a few ways to do this. I can say this, I can say left shift by 1, I can say mantissa equals mantissa plus mantissa itself. They're all the same, okay? They all get the same thing done. But if I do this to the mantissa, don't I need to do something about exp2? What should I do to exp2 so that the value represented would still be the same? Decrease it by 1. Okay, very good. Okay, so we say exp2 needs to decrement. Okay, there we go. So we get back here and go like, okay, so we need to compare the mantissa to something, right? So as long as it is less than something, we want to stay in that loop. It's not big enough. So what is that something? It's the largest value you can represent using a 64-bit unsigned integer divided by 2, right? So once again, we have u int, u int 64 underscore max, which is the constant defining that maximum number. And we say that as long as it is less than this whole thing, and we have to do a -1 here. Nope, we don't need that. I think that should be good. So if it is less than, I think we need a -1 over here. Because if it is exactly the same, then we are still going to, no, okay, that should be fine. Just that. So I think we got the other one done now, okay? Negative exponent of 10, should be done now. So let's go ahead and give it a try. Huh? On the right.
Your comment.
Oh, that's extra. Okay. You guys are very good at spotting these. Good job. Okay, so now we can run the code again, but this time we will change the number first. So we go to project, and then we set program's argument again, but this time we go for -40. So it's still 1.23, but times 10 to the power of negative 40 instead of positive 40. Okay, save that, and run it. And we are stuck in an infinite loop, or not. And then we want to look at the output. Okay. That looks about right. Yep.
The journal says that the inner loop should be as long as mantissa is less than or equal to largest numerator value -5 divided by 2.
Oh, right, because we have to make sure that there is room to, okay, got it. Okay. -5 divided by, it does it again. There we go. Okay, let's run it one more time. It's finished already, so it got out. Okay, let's put another breakpoint here. Okay, I think we got to the same result. So the question is that really representing the same value that we started off with, which is 1.23 times 10 to the power of -40? So how do we check? Spreadsheet, very good. So we copy this to this part here. And then we copy and paste this one to the second part. And it does not, oh, forgot about the sign here. Yep, there we go. So we got everything back. So do we have any questions about the code itself? I mean, your code doesn't have to be exactly the same, but you should understand, this code or how it is actually doing the same thing as your code. So are we good so far? Shall we move on to the normalization part? Okay. So before we talk about the normalization part using the program, I think the first thing we need to do is to talk about the whole process of normalization. What we have at this point, what we need to do, so that this way we kind of understand what the code is trying to do. So let's go ahead and do that, and we'll use Zerno for that. And maximize and zoom to page width. There we go. All right, so what we end up now is a 64-bit mantissa. So what we have now is a really long mantissa, 64-bit wide, and it is not normalized. In other words, the entire 64-bit unsigned integer is the mantissa, okay? But we also have an exponent in base 2, so we have 2 to the power of exp2. But this entire thing is our mantissa. Is that okay? This is what we have at this point. When that code completes, this is what we have. Are we good so far? If I want to draw the decimal point, even though it is implicit, where is my decimal point? This is a whole number, which does not have a fractional part. But if I want to draw a decimal point on this, in this picture, where do you think that decimal point is going to be? All the way to the right-hand side, right here. That's where the decimal point is, by default, right? Okay, so I'm going to use a red dot here to indicate this is where the implicit decimal point is. Now, of course, the name decimal point is not really relevant because this is a binary number, so I really should be using binary point. But nonetheless, the job of the point is really simple. It separates the quantity of 2 to the power of 0 from the quantity of 2 to the power of -1. That's the job of the point. Okay? So if I want to normalize the mantissa, what does that involve when I say normalizing the mantissa? Okay? So let me give you another scenario here. Okay, to the power of something. So what I want is I want this binary point, which was here, all the way to be here. It is sitting between bit 63 and bit 62. So how many times do you think I have to move the binary point in order to end up with a normalized format like this? I have to move it 63 times. Very good. Okay. So that means if I implicitly put the point over here, okay, in the lower picture, if I implicitly put the point over here, the exponent of 2, I need to do some adjustments to exponent of 2. Every time I move the binary point to the left by 1 position, what should I do to the exponent in base 2? Add 1 to it. And since I have shifted it 63 times, so I should be adding 63. Yep. So I take whatever I had and just add 63 to it. Is that okay? But have I done actually anything to the mantissa? Nothing. Okay? No bit has been moved with the mantissa. I am just saying it's a mental exercise. Originally, the implicit binary point was here. Now the binary point is now here. Are we still doing okay so far with this? Are we good? Okay. So then you look up the IEEE double precision floating point number format. how many places can we actually store for the fractional part of the mantissa? 52 bits. Very good. So what that means is we have a lot of extra bits that we don't need anymore. Okay? So what that means is I only need 52 of these bits. This I don't need because it is implicit. This is all extra stuff I don't need either. So the question now is, how do we make this look right? In other words, how do we move these 52 bits from where they are now back to where they're supposed to be? How many times do I need to shift to the right-hand side? 11 bits, 11 times. Okay? So the way you know how many times we have to do this is to look at this bit here. What is this bit, the most significant bit that we're losing? No, it cannot be 2. There are 53 bits over here, okay? So 11, exactly. So if this is bit 11, that means we have to shift by 11 bits. Does it make sense? Let me see, does it make sense? Just checking. Okay, so this is bit 63. This means this is bit 62. Bit 62 has to become bit 51, which means we have to shift 11 times. So that makes sense. Okay, I'm just double checking from a different perspective. So we have to right shift 11 times. So that means the mantissa has to right shift 11 times to put all the fractional mantissa bits at the right place. Okay? Well, this operation is really cool because it gets rid of all the bits to the right-hand side of the useful bits because they just got shifted out of the whole thing. What about the most significant bit here? How do we get rid of that one? And by the way, that one is guaranteed to be a 1 because at the end of the current algorithm, bit 63 was guaranteed a 1. So somehow we have to get rid of bit 52 after the right shift operation. How do we get rid of bit 52 after the entire operation? You can mask it. Okay, so that's a very good thing. So what is the bit mask? The bit mask is going to be run shifted 52 times because it's bit 52 that we want to remove. So it makes sense that the bit mask is this. Okay, so to make it more safe, we just cast it to a 64-bit number first before we shift it to the left-hand side. Then what do we do? How do we get rid of a bit? In other words, how do we turn a bit of 1 into a bit of 0? And we only want to impact one single bit. We don't want to change anything else. Yep. So we want to do a bitwise NOR first, which basically turns the whole thing upside down. Every single 1 becomes a 0. Every single 0 becomes a 1. Is that okay? So when you look at this portion, only 1 bit is a 1. Every bit out of bit is a 0. So when we invert it using the bitwise NOT operator, then all the 1s become 0s. All the 0s become 1s. So that means we have 63 1s and only 1 bit that is a 0, which is the 1 bit that we want to get rid of. Is that okay? So now what do? Well, we perform a bitwise AND with whatever mantissa has at this point. So what that's going to do is, okay, let me ask you this question. We know most of these bits are 1s, right? What is true and true? True. What is false and true? False. So it seems like and true is pretty useless. It doesn't do a single thing, right? It preserves the original value. So that's why this bitwise AND is going to preserve most of the bits of the mantissa except for 1, which is guaranteed to turn into a 0. Because whatever bit is a 0 in the mask, when you perform a bitwise AND, those bits, if there are multiple 1s, they become 0s. Because whatever AND 0 is a 0. Is that okay? So at this point, with this operation included, we would have moved the mantissa to the right place, get rid of the one that we do not need, but we still have the exponent and also the sign to take care of. Where is my exponent? This is my exponent. This is my actual exponent, but this is not what I need to store. The number that I need to actually store is what? It has to be biased by 1023. So that means our actual E value is exp2, which is what we have at this point, plus 63 because of this part here, and then plus the 1023, which is the bias specified by the IEEE standard. So we take this E, and then we have to move it to the right place. We have to shift it all the way to the right place. How many times do you think we have to shift it? Bit 0 of the exponent is bit 52 of the double representation. So we have to shift it 52 times, okay? So now we just say, okay, E left shifted by 52 times is going to give us the component for the exponent. There's one extra component left. What is that? The sign, right? The sign is, okay, if the sign is a 1, then we have that 1 to shift the sign. If the sign is 0, we have that 0 to shift. So that one is pretty easy. We just have to shift the sign, which is already either 0 or 1, 63 times. So it becomes bit 63. So now we got all three components, okay? We got this component, which is only the fractional part of the mantissa. We got this component, which is the exponent, which is also biased by 1023. And then we have this last component here, which is the sign. What should we do with all of these components? You can add them up, but the better way to do it is to do a bitwise OR. So you can do an OR, and combine them. So are we doing okay so far with the math, or at least the operations? More or less? Okay. All right, so let's go ahead and implement this. So we have to shift the mantissa 11 times to the right, and then we perform a bitwise AND operation with a mask, and then we do the E, and then we do the sign. Do you guys want to do it in one single shot, or do you want to do it separately? Separately. Okay, we'll do it separately. Okay, we'll do it separately first. And then we'll do it in one shot. Something is not right about this. Okay, maybe it's because the program is not terminated. Yep, there we go. Okay. All right, so we'll do it step by step. So the first thing we need to do is to right shift the mantissa. So PN mantissa, and we can do it like this. Okay. So we shift. Okay, we get rid of bits that cannot be represented. Okay. And then the next thing we need to do is to get rid of the most significant bit of the mantissa. So that means we have to do a bitwise AND with the mask that we just specified, which is the bitwise NOT of uint 64_t, 1 shifted 52 times. Okay. Get rid of the implicit 1 point. Okay. All right, so the mantissa is now ready. Let's deal with the exponent. Okay. Do you remember what we need to do to the exponent? We have to add two numbers to it. The first number is 63, because we are implicitly moving the binary point all the way from the right-hand side to between bit 63 and 62. So we have to do this one. Does it make sense? Yep, okay. And then we also have a bias. The bias is 1023, so that's why we have to add 1023 to it as well. So that prepares the exponent. But once we have the exponent, we can also just kind of shift it to the right place. So we can now say the exponent in base 2 is shifted 52 times so that it is now at the right bit position in the double. One last thing to do, which is the sign. So we have to, so the final answer, okay, which is UN64_T, this is a local variable. Actually, this is not going to work, but we'll do it this way. This is the actual double representation, and then we'll use that. So double representation. Okay, so now we have all three components. We have the sign, which has to be shifted 63 times, and it is best to cast it to an unsigned 64-bit integer first. And then bitwise ORed with PN exp2. And because exp2 is a 16-bit number, I can't really do it this way. So sorry about this. I can't really do it this way because it's only a 16-bit number. So we have to do the shifting here after I cast it. So UN64_T, and then shift this 52 times. And then bitwise OR with Mantissa. Mantissa is already prepared, so we can just use Mantissa as it is. Do we have any questions about this part? Does everybody kind of see, at least in general, how these lines of code from line 38 to line 42 is kind of doing the same thing as what I showed here by hand? Yep.
I may have missed this part, but can you explain again why you add 63 to the 2's exponent even though you just truncated 11 bits?
Correct. Okay, so that has to do with the original Mantissa has 64 significant bits, significant digits, right? But the implicit point is all the way here. To make the Mantissa normalized, I need that point to be all the way over here, with only one bit to the left-hand side of that point, okay? But every time I move the binary point by one place, it is the same thing as halving or dividing the Mantissa by 2. But each time I divide the Mantissa by 2, I have to add 1 to exp2. So now the question is, how many times do I have to move this binary point in order for the binary point to get here?
So you're just cutting it off. Assuming those would be 0, you don't know what they are because they don't fit.
Which ones?
The 11 that you truncate.
So these bits that I'm truncating, they may not be zeros. It depends on the conversion process. So the conversion process is keeping more digits than I could possibly keep, because that way, as I keep working on the number, I do not lose precision as much. In other words, I try to use as many bits as I possibly can during the conversion process. It's only when I absolutely need to get rid of bits, then I look at it and go like, well, I'm sorry, I don't have enough bits to represent everything. So at that point, I have to truncate. So instead of truncating as we do the calculation, which will end up with a less accurate calculation, I only perform the truncation at the very, very end of the entire process. Does that make sense? Okay. And then the other thing is, if you're performing addition in 52 bits and you're performing operations in 64 bits, do you think it makes any difference in terms of time to process? It doesn't make any difference, because internal to the processor, the pathway the size of the ALU, the size of the adder and the subtractor and whatnot, those are all 64-bit anyway. So when you're doing a 52-bit number addition, it takes exactly the same amount of time as performing a 64-bit addition. So it doesn't gain anything if I try to truncate early. Is that okay? All right. So are there any other questions, mapping this diagram to the code that I have here? No questions? All right, well, it's time to let it run and test it, right? Well, we always want to test it, gotta make sure. Okay, so let's go ahead and run with the same number as before. Okay. No. Now, why is the build failing? Okay, program has stopped. Oh, okay, there's an error on this line. So let's go to build log. That thing shows. Is it because of the parentheses again? On which line? It looks like it's on this line here. Oh, an extra one? I can't see the error message, which is kind of awkward. I don't see the error message. Huh? This equal sign? Oh, this one? That usually would not give me it's incorrect to have that equal sign, but it should not give me a build problem. But it did. Okay, all right. Okay, let's run it. The user interface is having a problem. This is where the first breakpoint is. Continue execution to this point, and then we just single step through it. All right, so now we can take a look at double wrap. Okay, and we want to print it as a hexadecimal number. And it looks reasonable. Okay, so how do we know whether this number is correct or not? Whether the representation is correct or not? How many people remember the trick of casting the address of a 64-bit number to the address of a double and then dereferencing it so that we can actually interpret the bit pattern as a double? Nobody. You got it down. Very good. Okay, so let me see if I can remember that too. So we'll say we're dereferencing double pointer, and it is the address of double wrap. Okay. Nope, doesn't like that. Oh, I'm missing one paren. Okay. The address of double wrap. Close. There we go. Pretty close. So are we doing okay so far? More or less? Okay. So I think my code blocks may not be configured correctly in some way, because it's not supposed to like pause like this, and the scrolling is way off too. It doesn't scroll correctly. Normally I use VI and make and just hand enter the GCC commands. But this turns out to be more difficult. Okay, so are there any questions about the solution? Any questions about the normalization part of this?
When you were moving the EXP2, the question that she had, if you go back to your journal,
Go back to the journal.
yeah, where you drew it out, the little,
Oh, okay, journal.
yeah.
Yeah.
So right here, when you added the 63 to the EXP2,
Mm-hmm.
that's basically dividing by 2, right?
No, this is like, because I have divided the mantissa, at least conceptually, I have divided by 2 to the power of 63 in order to move the binary point all the way from here to here. Is that okay? I think that may be the most difficult part to understand because the point has never been explicitly represented, but it is implicitly here originally. So if I want to change the position of the point all the way to here, then the value of the mantissa is going to be divided by 2 to the power of 63. So in order to compensate for that division, I have to add 63 to the original EXP2. Is that making, is that connecting?
Well, in the code, you add the 63.
Yeah.
Where do we divide the mantissa?
It never really happens. That's the whole point. Because that never really happened. Because okay, let me just kind of draw the finalized picture. So when you look at the entire picture of a double, okay, so we look at an actual double, okay, we have 53 bits here, which means it goes from bit 0 to bit 51. But what this portion is representing is the point blah, 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 blah of the mantissa. The 1 of the mantissa all the way to the left-hand side is never represented. Is that okay? So we want whatever we had to resemble this particular format. So we want to put that point, which is implicit, all the way here. So we have to shift the whole thing first to get rid of the digits that we have no place to represent, and then we have to move the point. So you can do those two operations in opposite order. Okay, you just have to adjust the exponent of 2 differently, but you still have to go through that process. It's just that you can do one first or the other first. Doesn't really matter which one. Is that kind of explaining what it is? And then we have 11 bits here. That's E, which is the biased exponent. And then we have 1 bit here, which is our sign. So that's what a double looks like in terms of how the bits are used. So are we doing okay, or do we need more explanation with this? Yep, go ahead.
When it gets to the point where you're combining it all into the double rep variable,
Uh-huh.
how did you shift the E down enough points so it ends up in the right place?
I shifted up.
Oh, okay.
Yeah, I shifted to the left by 52 positions.
Okay.
Because those 52 bits are used by the mantissa as the fractional part of the mantissa.
The distance to that part.
Yep. Mm-hmm. Any other questions? Yes?
Can you go back now to where you initialize the, not initialize,
Declare? Yeah, it's just a 64-bit unsigned. Any other questions? No other questions? So you can expect at least one question related to double conversion in exam 2. And you won't be able to run this code, okay, unless your brain works like a processor. This code may not be very helpful, but understanding how this code works is going to be helpful because you'll be understanding, oh, we are looking at a mantissa, there's an exponent of 2, and how do these things relate? What is the actual value represented? So that's going to be helpful. So being able to understand this code is going to be helpful, even though you cannot actually run this code in your head. Very few people can do that, but yeah. So are we good so far? Any questions before we move on? No questions? Okay. Okay, I got one thing to do. Oh, maybe not. Maybe next time. I was trying to compare the accuracy of my conversion logic to the internal conversion logic of C and C++. Because if I remember correctly, my conversion logic is actually more precise than the internal conversion process of the C library. Because I think they do some truncation too early. As a result, they lose precision in the whole process. Okay, so that part is done, and we can now move on to the last part of memory stuff. Okay, we got quite a bit of time. All right, so we're getting back to D flip-flops. And if I remember correctly, last time we were already talking about this circuit, which is a clocked and gated D flip-flop. Yes? And I equated, did you guys remember the analogy? What example did I use to explain a clocked and gated D flip-flop? A camera, digital camera, exactly. So as a digital camera, your data pin is kind of like the lens, okay? It is observing, something on the outside, but is it going to capture that? Your Q is basically the storage in the digital camera. Am I capturing the image, okay? So that's the question. When do I capture an image? When do I capture the next image? The enable line is kind of like, is your camera on? Okay, so if the camera is off, you can click the shutter release all you want, nothing happens, okay? So you have to turn on the camera first, enable. The shutter release is your clock, okay? When you have that click motion on the shutter release, that is the moment that your lens, which is your data pin, is going to capture whatever it is seeing or whatever it's sensing, and it is going to remember that as Q. But after that moment, you can hold the shutter release button down all day long, and it's not going to capture another image. You can release it. The release of the shutter release button is also not going to capture any additional image. It's only when you press it down, then it will capture an image. So it's only edge sensitive to one direction. So are we good with that concept? Yes?
I built it in Logician.
Uh-huh.
And to me, it seems like enable and clock input, they work.
Inverted?
Same.
They're the same?
Yeah. So basically, I tried to play with enable button. So I changed data from 1 to 0, from 0 to 1.
Mm-hmm.
And when my clock is on, and then enable, I turn it back to 0, and then 1, and then Q changes. Then I tried to play with clock, and it's acting the same way.
It should not behave like that. So I have to check that. I'm fairly sure I checked this already because that's where I capture the image, but I can check it again. All right. So assuming that it's working, okay, let's move on to the next one. What has changed this time? How many input pins do we have this time? We got 4 input pins. Okay. So let's look at the names of those 4 input pins. We got clock, same as before. We have EN or enable, same as before. We have data, same as before. The additional pin is reset. You cannot see that on the other side of the edge. I can, where's the remote? Right here. So sometimes it's only because it doesn't do the auto setup correctly. Okay, much better. So this time we have one extra pin, which is called the reset pin. So what the reset pin does, okay, so let's take a look at the reset pin and see whether we can explain what the reset pin does to the entire thing. The reset pin bypasses a whole bunch of circuitry, which we have seen previously, and it goes straight into a OR gate through a negated input and an AND gate, which is through a non-negated input pin, okay? what does a 1 do with an AND gate? Nothing, right? Because anything AND 1 is the original thing. So it doesn't really impact. Whatever is coming in is going to be going out when the reset pin is a 1. What about the OR gate? Well, before it gets into the OR gate, it is negated. So if reset is a 1, by the time it gets to the OR gate itself, it's going to be a 0. So what is OR 0 going to do to a value? Nothing. It's not, well, not 0. It's going to preserve the value. X OR 0 is X. Because true or false is true, false or false is also false. So anything or false is preserving the original value. So that means when the reset pin is a 1, it doesn't do a single thing. It doesn't do anything at all. It just preserves whatever is coming in, and it just gets passed through to the S and the R pin. No big deal. What happens when the reset pin is a 0? Well, that's the big deal, okay? When the reset pin is a 0, then A3 is guaranteed to output 0. What about O1? It's guaranteed to output 1, because when reset is a 0, it is negated first before it gets into the OR gate. So that means whatever value is getting into the OR gate is a 1. Anything OR 1 is a 1. So that means A3 is guaranteed to output a 0, and then O1 is guaranteed to output a 1. What is that going to do to the SR latch? It's going to reset the output of the SR latch. So it's going to reset Q, which is the final output. That is why the reset pin is called the reset pin, because it guarantees the actual memory device, which is the SR latch here, is going to be reset. But why is that important?
Put something in the starting state, a known state.
Yep, it puts the register into a known state, which in this case is 0. But why do we want to be able to put a register to a known state using a single pin that is level sensitive? Why is that important? What happens? Yeah, go ahead. When you first turn on your computer, exactly. So when you first turn on your computer, without the reset pin, without the mechanism to reset, what do you think would be the state of all of these SR latches? They're all unknown. Some may be 1, some may be 0, okay? Some may be oscillating, remember? Okay? So it can be anything. Well, if all the registers, if all the memory capability of your computer is randomized when you first power up your computer, how do you get control in the first place? You cannot, okay? Because all the instructions they want to execute are random bits. Where is that starting? Where is your processor going to start executing? A random location in RAM. What is the content of that random RAM location? Random. Okay? So that means we need to have some initialized state that we can actually count on. So that's why all the registers inside the processor, they all have a reset pin. So when you first power up your computer, those registers are guaranteed to be zeros. Your processor is guaranteed to start execution at a certain location with all the registers pre-initialized to 0. So that's important, okay? Second question. So who's in charge of this reset pin when you're first powering up your computer? Because how many people have a computer where the instruction of starting up the computer involves press the reset button, hold the reset button while powering up, wait a second first, and then release the reset button? Does it come with instructions like this on your computer? No. So who's holding that reset button? Or what is holding that reset button? The power supply doesn't do that. There's a specialized chip on your computer called a watchdog chip, or otherwise known as a supervisor chip. So what that chip is going to do is it will monitor the voltage from the voltage regulators. Okay. So when you first power your computer, the transformer, the regulators, it will gradually ramp up the voltage, okay? So until the voltage coming out of the power supply reaches a threshold for a certain amount of time so it's stabilized, that reset is held down by analog circuits, okay? Now, what happens when you have a brownout? What is a brownout? How does it compare to a blackout? It's not exactly a glitch. It's your power. Okay, so the wall outlet normally outputs what, 115 volts AC. So a blackout means it's out, zero, okay, in a very short amount of time. Yes? It's basically, it's going low, but it's not out entirely. So it goes down to maybe 50 volts instead of 115 volts. It goes down to 50 volts, okay? And then it goes gradually down to like 40 and then 30 and so on. So the power supply of your computer would also kind of fluctuate because of that. So what the supervisor chip would also do is when in that situation, when the output from the regulator drops below a threshold, then the reset line is also going to be held down. Because below a certain threshold of the power supply, the behavior of the transistors inside the processor is going to be unpredictable. So the supervisor chip is basically a analog circuit on your computer, inside your computer circuit, to make sure that it only operates when the power supply is healthy. So that's a very important part of your computer, because without that, your computer can glitch all the time. All right. So let's take a look at this circuit here. So within this circuit, all of these rectangles, they are the final version of the D flip-flops, okay? What do I mean by the final version? They are the level-sensitive, edge-sensitive, resettable D flip-flops, okay? But when you look at this picture, the first time you look at it and go like, wow, that's really a mess. But it really is not that big of a mess, okay? Because you can see that only the pins coming from D, or the wires coming from D, are going to individual registers only, okay? And only the Qs out of the registers, are out of the D flip-flops, are going to the output individually. When you look at the clock pin, how do you think the clock pin on the left-hand side is connected to the individual clock pins of the D flip-flops? They're all the same, okay? Now this type of configuration is also called a multi-drop topology, where one pin is connected to all of the other pins, okay?
Would it be called synchronous then?
Synchronous describes the operation of the D flip-flop over time. It only changes when we have a transition, so it doesn't describe the topology of how the wires are connected, okay? What about the enable pin? How is the enable pin all the way to the left connected to the enable pin of each D flip-flop? Same thing, same topology, it's multi-drop. What about the reset pin? The same thing. So this configuration is known as a multi-bit register. In other words, what we see or what we call a register is nothing more than a multi-bit D flip-flop, where the enable pins are all connected to one single thing, the clock they're all connected to the single pin, and then the reset are all connected to the single pin. Is that okay? And why do you think this is important? It is the most basic memory devices of your entire processor. Okay? So before this picture, we have the picture of an adder, right? So we have the capability of, okay, here's X, here's Y, and this is the sum of those two numbers. Or you can easily reconfigure it to become a subtractor, okay? So we have X, we have Y, and then the output is the difference between X and Y. But just being able to do that calculation is not going to be very helpful if you cannot remember the result and use it in a later calculation. Does that make any sense? This is the first time we encounter a component that can actually, quote unquote, remember, okay? So just kind of imagine that the D pin here is connected to the output of an adder, okay? So let's say we have an 8-bit adder. So these D pins are, D lines are connected to the output of the adder. So now, when we have enable being a 1, reset being a 0, being a 1, and then we have a rising edge, then that result of the calculation can then be stored into these 8 D flip-flops. Okay? You can have, then you can turn off enable. Okay? You can turn off enable. So from here on, the output of this particular setup is going to be the same thing regardless of what you do, on the other side. And this is the most basic way to remember the result of a calculation. Yep. So this is only accessible by the processor? This is only accessible, it's a component inside the processor, and then there are registers that are software accessible, and then there are registers that are not software accessible, at least not directly.
So kind of what I was wondering is like your RAM and like ROM.
RAM is different. Yeah, so RAM is different. The way RAM, remembers content is a little bit different from a register, but it does have, almost exactly the same kind of logic. But the configuration is different. And that's why you only have like 32 registers inside the processor, but you can have gigabytes of RAM, in a computer, because the configuration is slightly different. And there are 2 different types of RAM as well. You have static RAM, and then you have dynamic RAM, which we know as DRAM. All computers that you use today, they all use DRAM, which stands for dynamic RAM. So what do you think is the difference between dynamic RAM and static RAM? One is an extrovert, the other one is an introvert. Okay, which one is faster? DRAM is actually faster, but that's not why we call those DRAM or dynamic RAM. So the difference is with static RAM, they can maintain content without any clocking as long as power is still supplied, okay? Static RAM can just go like, okay, I don't need to do a single thing, and I can maintain the state of every single bit. Dynamic RAM, on the other hand, needs to be refreshed. So it needs to be refreshed periodically in order to maintain its content. And that's why it's called dynamic RAM. But dynamic RAM has a higher density, which means you can pack more bits of information into a smaller package. So that's why we all use dynamic RAM on most modern computers. Except when power consumption is really, 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 really important, then you use static RAM. Because static RAM can use like this much energy to maintain its state, when dynamic RAM cannot really quite do that. It still needs to consume quite a bit of power just to maintain its content. All right, so that's the end of today's lecture. I do not have any lab for you guys to do just yet. So, you can go to the lab. I'll be over at the lab if you want to review, content in this class.